Okay, hello, here we are. 5.7, 2.7 exponential growth and decay. You guys, this is the third time I record this video. Everything's getting crazy up in here, so let's get this one done. Alright, exponential and growth and decay word problems. There's three different formulas, but as you can see, they're all pretty similar. We have our exponential function, which has some base here to an exponent. And so the regular exponential has the base b to an exponent x. F of x is the function, meaning you're plugging this x value in to get the total f of x. P is my initial value. And so I have all these words up here, just so you can pause it and read through them. I'm not going to read them all, but it's mostly just sort of an extended version of what I say. So P is the initial value in these word problems. And x is usually time, and then f of x will be the function at that whole time. When I talk about growth here and decay, there's rates of growth and rates of decay. And so growth is obviously increasing at the same rate, but exponentially. So that means not linearly, not like rise over run, but at this sort of rate. And then same thing with decay. And so you'll notice that these equations are the same thing as the exponential, except this b turns into this 1 plus r and this 1 minus r. And so rate is in a percentage, okay? And so when I have like a 2%, that's the rate of growth. But it's increasing not from 0, from 100%. And so I sort of explain here that it's increasing from 100 or percent, which is the same thing as a 1, right? If I move the decimal place over 2. And so I have this 1 here, which means like 100% plus whatever other percent. So at this rate, I'm going to have to change into a decimal as well. For the exponential decay, it's the same thing, except you're subtracting the rate from 100%. Okay, and so that's sort of the difference there. So let's try some examples really quick. Alright, so my first example here is an exponential growth, and I have two exponential growth and an exponential decay. And this one already has the function given to us because I just want to sort of look at what this means. And it also has a base of e, and so we've talked about this, and so it's not necessarily looks like the three equations we just talked about, but it still is an exponential growth. E is our base, some exponent with a variable in it, time here, if you read the problem. So this says if the population of the U.S. continues to grow as it has since 1980, then the approximate population in millions of the United States in year t, so t is talking about years, time, and so t equals 0, which is the first year, or like where it started, I guess not after the first year, but before it, corresponds to the year 1980, right? So these go along with each other. And so it's given in this sort of function. And this p is sort of confusing because we used a p in the other one, so let's just call this k. Alright, so what is the population of the United States in 1980? Okay, well 1980 is our initial year, right? And so this whole function is talking about population. And so at this year 1980, which is 0 really, if I plugged in a 0 here, I get an exponent of 0. This turns into a 1. But also we know that this value is the same as this value p, and this value p, and this value p, because it's outside of the base. And so this is my initial value, which is 227 million. That's where it starts at, because this is the number outside the base that's multiplied by it. Okay. Estimate the population in 2015. And so this is saying estimate the population. And so this is asking for what is the function k at a certain time. And the time is in the year 2015. Alright, but we have to pay attention to this where t equals 0 is 1980. So I'm not plugging in 2015 into this function. I need to find out how many years it's been since 1980. And so I can subtract 2015 minus 1980, and I end up with 35 years. and that's going to be my t value here, my time. And so I plug in up here, so I have k of 35 equals 227 times e to the 0.0093 times 35. And so I need to evaluate that. So if I go to my calculator, just on this particular one, I have to do the exponent first, so I'm just going to multiply 0.0093 times 35, because I can't figure out the parentheses. Anyway, so I get 0.3255, and so I need to add that in the exponent. So evaluating my whole function now, I have 227 times e raised to what we just calculated there, so 0.3255, because that's what we had in our exponent. And you get about 314.3, and that's how many, the population after 35 years in 2015. So my k value, or my population, I changed it to k, but I confused p, is 314.3 million. That's the population at that year. Okay, so general sort of overview. In the next one, I'm now going to have to create the function. All right, and this has some more advanced. This is one more advanced. So the world population. Talking about population again, there's more than just population and exponential growth, but these were two good examples to show. So the world population in 1950 was about 2.5 billion people. So you'll notice this one starts at 1950, not at 1980, and has been increasing at approximately 1.85% per year. Okay, so this we know is my rate, right? We're thinking back to this exponential growth function, because now you'll notice in A it says write the function, so we have to actually create our function equation. And you'll also notice that this 2.5 billion is going to be our P, or our initial value. So if you remember back to our exponential growth function here, we're going to use this one, so we can plug in what we know. So we have f of x equals P, our initial value is 2.5, we said here, 1 plus the rate. But I can't enter in the rate as a percent. So remember, I have 1.85. I need to move that over 2 decimal places. So this is actually plus 0.0185 all to the x. So this function is going to depend on this year x. And I do need to simplify here. So f of x equals 2.5 times 1.0185 to the x is our function. So that's our answer for A. All right. B, estimate the world population in 2015. All right, so this is very similar to what we just did, just with this function up here. And you'll notice, though, that, remember, this one started at 1950, so we have 2015. We have to find the time, or the x for that. And so, and you could have, no, sorry, you could, okay, what was I saying? We need to find the time. Okay. So 2015 minus 1950, because this time that's where we start. And so this time we're finding it after 65 years. Sorry, okay. And so I plugged that in, so I'm not going to actually show this, we'll just plug it in and give you the answer because we know this already. So you say 2.5 times 1.0185 to the 65th power. When you plug that into your calculator, you should get about 8.23. This one's in billions. So that's our population in 2015. All right. C is a new type. Okay, so this says in what year? Year is x values, right? So we're solving for x here, which is different. In these problems, we were plugging in an x, okay? So in what year will the population be double what it is in 2015? So we need to figure out what that population is, and that's going to be our f of x value, okay? And we're going to plug that in for f of x because that's our final population, and then we're solving for the year when that happens, okay? So the double the population in 2015 is double this, 8.23. So if I have 8.23 double it, multiply by 2, I get 16.46. And that's going to be our f of x value. So I plug that into my function, I get 16.46 equals, all right, and so you can use two different things here. Double what it is in 2015, and so I'm going to use my initial value here as what it is in 2015. So I'm going to put an 8.23 here, okay? You could plug in 2.5 and you'll get the same answer. You'll just have to do a different thing in the end, and so I'll sort of go through that. So I'm using 8.23 because this starts in 2015. Alright, so this rate and all that, those are the same. So it's 1.0185 to the x. And so we need to solve for x. This is what we talked about in lesson 2.6 or 5.6, okay? So this is from that 2.6 video. When I have an x in the exponent, what do? I need to use logarithms to bring this down to the coefficient. And so what I need to do first is get this term by itself. This 8.23 is just multiplied. So I divide this 8.23 on both sides. Those will cancel. And now this we should already know here from this calculation becomes a 2. And I have 1.0185 to the x, okay? And so what I need to do is use that LOL3, but to do that I have to add log to both sides. So I can add log to both sides. When I do that, this x becomes a coefficient. Sorry, it's not on the left side of the equation. So I have log of 2 equals x now, because this comes down, times the log of 1.0185. Okay, and so again we're trying to solve for x, so we're going to divide by this log of 1.0185. Okay, when you do that on your calculator, I hope you'll go through and do that, you get x equals 37.8. Okay, and so that's a years, right? 37.8 years. But read the question. The question says, in what year? And so that means in what year, and here I started with initial value of 2015. So this 2015, I need to add on the 37.8 years, and that's going to get me the year, in what year this population doubled. Okay, and so when you add that, you get 2052.8. And so in what year? Well, that's in the year 2052, right? Because this is somewhere in that year. It doesn't ask for a month or anything specific like that. So quickly going back to what I said before we started this, I was talking about this initial value. So you could start with the initial value of 2.5. That's fine. You'll get a different answer here, but you should get the same final answer. Because this 2015 you wouldn't have anymore. You'd be adding 1950 plus whatever value you got. Okay? So you can do that either way. Alright. Exponential decay. Let's roll some dice first. Okay, let's change this. Alright, enter that in your CPP. So exponential decay. So we remember now that this function has f of x equals p times 1 minus r to the x. So we're subtracting the rate. Okay? And so this problem is a little bit different. It's a tricky problem for sure, but we're going to be able to do it. Alright, so when tap water is filtered through a layer of charcoal and other purifying agents, 30% of the chemical impurities in the water are removed. If the water is filtered through a second purifying layer, 30% of the remaining impurities in the water are removed, and so on. And so this part is sort of all one thing, describing these layers that are purifying the water. And all this and so on just describes what exponential decay is. It's decaying at this same rate, and the rate is 30%. Okay, and so to plug in here, I have f of x equals my initial value times 1 minus, our rate here is this 30% that it's decreasing by. And so this is that 0.3 when I move this decimal over. And so f of x equals p, 1 minus 0.3 is 0.7 to the x. Okay? Alright. So this 30 and 30, all that is describing that exponential decay. So the question's asking, how many layers are needed to ensure that 95% of the impurities are removed from the water? Okay. How many layers are needed? You'll notice that this problem doesn't talk about time, it talks about layers. What affects this function is layers, and so how many layers is going to be an x value. That's our x value. Right? So it's asking for x here. And so what this problem doesn't give us is an initial value, this p. So because when it starts as tap water, it has all this impurity, 100% of impurity, and so it's taking it down 30% each time, right? And so this p is sort of like a 1 value. And so when it doesn't give you an initial value, you don't have to use it. It's just like a 1. And so my function here is really just 0.7 to the x, okay? So we need to figure out, though, what we're solving for. So this question says, how many layers are needed to ensure that 95% of the impurities are removed from the water? Okay, so this 95% is the function, is our f of x, all right? How many layers? It's asking us to solve for x. So how many x's, how many layers will we need to make this f of x a 95% removed? Okay, it's important this removed because we're talking about decay. So this is not just 95%, it's that 1 minus 0.95, right? 95% turns into 0.95. It's 1 minus the 0.95 because it's decaying there. And so it's asking, when will the function have this 0.5 only left of impurities? And so this 0.5 is our f of x. How many x values, how many layers are going to give us this 0.5? So I have 0.5 times equals 0.7 to the x. Okay? So, I know that's difficult. Rewatch it. Look at it again when you're doing these problems. Again, I have an x in the exponent. The only way to solve is to bring it down to the front. So I have to add log to both sides. I'm going to use ln this time because you can use either. So that x comes in front. Now I have ln of you know what? This is 0.05. I hope you all caught that. Miss Schulte's sometimes wrong. Nobody's perfect. Okay. Equal. So now this x comes in the coefficient, ln of 0.7. Okay, so again, I want to solve for x. I have ln of 0.7. Okay, these divide. When I divide this on my calculator, I get about 8.4. Okay, and again, I hope you're doing this on your own to check that. But again, this is talking about layers, right? So it's a real world problem. We need to read the question. How many layers are needed to ensure that 95% of the impurities are removed from the water? So how many layers are needed to ensure this? Well, it's not 8 layers, and it wants total layers. It's not 8 because it's more than 8, and so the answer should be 9 layers is what you'll need to ensure, right? It says to ensure that 95% of them will be removed, and so the answer is 9 layers. All right? All right, you guys can do this section. Have confidence. We'll talk about it in class. Go through some problems. All right, see you in class. Shout out to JB.